Hydrogen-like atom in its ground state is excited by means of a monochromatic radiation of wavelength 975 angstrom. How many different lines are possible in the resulting spectrum? Calculate the longest wavelength amongst them. You may assume the ionization energy for a hydrogen atom as 13.6 electron volt. So for this problem, the first thing that we are doing is we are given that monochromatic radiation of wavelength 975 angstrom is the reason behind the excitation of a hydrogen atom which was initially in its ground state. So I can calculate the energy equivalent to this wavelength, which is going to be 12400 by wavelength in angstrom. So the value will be obtained in electron volt. So if we do the calculation, we can write it as 12400 by 975. So we obtain a value equal to 12.75 electron volt. So this is the first thing that we have obtained. Now the question is asking how many different lines are possible in the resulting spectrum. So from here we can say that the value for energy, that is 13.6 into 1 by n1 square minus 1 by n2 square. This value is going to be equal to 12.75 electron volt. So from here we are saying that n1 is equal to 1 because the question is saying that it was in its ground state, that is n1 was equal to 1. So from here we are calculating for n2. So we can write this equation as 13.6 1 by 1 square minus 1 by n2 squared is equal to 12.75. And then from here we obtain n2. So we obtain n2 is equal to 4. Now from n2 equal to 4, so we can consider it in this way, that for the n value equal to 4, we can draw it in this way, that this is equal to n equal to 1, n equals 2, n equals 3, and this one is n corresponding to 4. So the possibilities, if we look at the different transition lines, so the different transitions lines can be like this. So one is coming from here, another one can be like this, and then from here it is like this. So it can be n from 4 to 2 and then from 2 to 1, or it can be. So we have obtained different possibilities over here. So the different possibilities which we have obtained over here is 6 in number. So we have covered all the possible transition lines from n equal to 4 to n equal to 1. So the number of possibilities is 6. So number of possibilities can also be calculated by the formulation n minus 1 by 2. So over here I can cross check it in this formulation, 4 into 4 minus 1 by 2. That is, we get something like 6 transitions. So the number of transitions can be calculated by this formula, that the number of transition is equal to n minus 1 by 2. Now for the longest wavelength, the frequency should be the smallest. So for the problem it is stating, calculate the longest wavelength amongst them. So for the calculation of longest wavelength, the frequency must be smallest, and we are saying that it corresponds to the transition from n equal to 4 to n equal to 3. So it is corresponding to the transition from n equal to 4 to n equal to 3. So over here we can calculate it in very simple terms, that the energy corresponding to the fourth one is going to be equal to minus 13.6 z square by n square. So using this formulation we can write it as minus 13.6 1 upon 4 square, and on calculation we obtain it as equal to minus 0.85 electron volt, and the energy corresponding to the n equal to 3 can be calculated as minus 13.6 1 upon 3 square, that is 9. So we will obtain the value equal to 1.51 electron volt. So minus 1.51 electron volt is the value corresponding to n equal to 3. So if we subtract the two values, we obtain delta E, which is equal to 0.66 electron volt. Now the question is asking us to calculate the wavelength corresponding to this. So we can calculate the wavelength corresponding to this using the same initial formula which we have used, 12400 by wavelength in angstrom. So from here I can calculate that the wavelength in angstrom is going to be equal to 12400 by 0.66. So if we calculate it, we obtain value equivalent to 18787 18787 angstrom. So this is the value for the longest wavelength amongst them. So the question is completely done now. So I think you have made sure how to solve this kind of a problem.